Hey everyone, this is another question for Sean. So, Sean, this time
Yes.
the scenario is like this. Um, so you have, uh, we're, this is during the apocalypse, and the world queen has decreed that uh, all families must have at least, or must have only one girl to stop overpopulation.
Okay.
So what happens is these families will keep having children. So if they have boys, they will keep having children. If they have a girl, then they will immediately stop.
Okay.
So, given that there are uh, n families from the start,
hmm
what's the boy to girl ratio um, by the end of, or in the future, I should say.
What is the boy ratio
Yeah,
when every family has a girl?
yeah.
Boy girl ratio. Okay. Let's see. So I guess this is a probability question. Mm, there's n families, so the chance of having either a boy and a girl, chance
Mm-hmm.
is one half, right?
Mm-hmm.
Um, okay. So let's see. I'm gonna write some examples,
Mm-hmm.
so maybe that will paint a picture. So let's say n equals to 1.
Mm-hmm.
Chance of having a boy or girl.
Actually, let's start with a bigger
Let's
example. One,
yeah,
like,
yeah. So like theoretically,
yeah, 10.
10.
Yeah, that's fine. And then,
So,
so
oh man,
if each of the families were to have children, and the chance of them having either a boy or a girl is equal, then what's the expected
Mhm.
outcome at the end of this round?
Right. So for the first round,
Yeah.
you have if it's a
Mm-hmm.
boy and girl, you stop.
Mm-hmm.
For the second round, this boy and girl. Hmm, interesting. So a family can have keep having boys.
Mm-hmm.
Boy. Oops.
probably don't want to draw everything out, but like, is
I'll
there?
do it. So if the person had a girl in round 10, that means it is 9-1 boy-girl ratio.
Mhm.
So let's say,
Wait, but why is it? So you're saying if there was if one family had a girl and all of them had boys, right? But is that likely, given that the chance of uh, having both? Yeah. So what's the likeliest outcome?
oh, okay. So for round 1,
Mm-hmm.
there'll be 5 boys
Yeah.
and 5 girls.
Uh-huh.
I guess like round. Yeah, I guess I represent this graph. So 5 boys, 5 girls.
And then
Say round 2,
mhm.
be like 2.5 boys. 2. Let's
Okay.
just do theoretical now.
Yep.
Girls.
Mhm.
Round 3 would be 1.25.
Mm-hmm.
About 1.8.
Mm-hmm.
Round 4. Well, you can't have like
Yeah.
0.75 boys. So maybe it ends at round 3. Or ends at round 4.
Mm-hmm.
Does it?
Well, if the families, well, they have to stop having children once they have a girl, right? So
Right, okay. Yeah, so the question is how many rounds, right?
or no, so what's the ratio? Yeah, of boys to girls when they all stop.
Got it. So can we assume that once the number becomes less than 1, for a very big number, we can round to a girl has appeared?
Sure, yeah.
Is that a fair assessment to make?
Yeah. Well, because I mean, it's even though the chances are equal, you can't have 0.5 of a child, right? So
okay,
I mean, it would either be one or the other. Yeah.
Value is less than 1. We have a girl.
Okay.
Okay, so in this case, n equals to 10. So I'm going to sum them up.
Mm-hmm.
I will assume round 4 is just 1 girl.
Yeah.
So like about 1 girl.
Okay.
We have 5. Oh man. 7.5. 8.75. Actually, what if I added this just to my calculations? So, so 7.5, 8.75. That's 9.5. So 5 boys.
Okay.
And then 5, 7.5. I guess it's the same.
Mm-hmm.
Girls.
So can you generalize or can you explain what's going on here? How come? So
Yeah.
how
So
come? Yeah, explain why that
yeah.
policy didn't work.
Okay. Yeah. Um. So the reason why it's equal is because families that have a girl will stop having kids.
Hmm.
So having a girl guarantees there's no more boys for that family.
Hmm.
So for each additional girl, you have theoretically a family that keeps having one more boy, another family that keeps having one more boy if the last one was a boy.
Hmm.
Um,
But how come? So each family only has one girl, right? But then some families have more than one boy. So how come the ratio is still the same?
um,
I mean, it's right. I just want you to explain it.
let me complete this graph.
Okay.
That may help you with some social.
I think a better way uh, to do this is to so maybe like how I would represent it would be to use a outcome tree.
This part.
Yeah. Or I mean like a tree basically, a sideways binary tree.
Let's see. Well, I think I can explain by just looking at this. So, like round one makes sense because the possibility of having a boy or girl is half.
Mm-hmm.
Um, if you so now you've taken all the families. So since each time the probability of having a boy or a girl
Mm-hmm.
is half,
Yeah.
even for the people who kept uh, giving birth because of the boys,
Mm-hmm.
the probability is still half.
Mm-hmm.
Um, so in that sense, it doesn't really matter if you need to stop by having a boy or a girl.
Mm-hmm.
Um, if there was even if there was no rule to stop, it would
Mm-hmm.
still be about the same.
Okay.
Um, so
So because here you're just looking at the generations, right, and not at
right,
the so ignoring the number of families having children, if you look at each generation, it's about roughly the same, right? Okay. Yeah, I think that's it.
okay,
Okay. Um, let's
this is easier
see.
than I thought.
Yeah. You did well. So it's good that you clarified whether having a boy or a girl, um, whether there's an equal chance of having a boy or a girl. Because this I didn't tell you. So it's good that you didn't assume you asked. That's it.
Okay, all right. So
I'm gonna.
yeah, I think it was helpful that you told me to list out the generations here.
Mm-hmm.
I would have done it a different way, but I think this was probably clear.
Yeah. Okay, I'm gonna stop the stream now. So thanks everyone for joining us. Hey everyone. So this time we have another question for Sean. Um, So Sean, the question is, imagine a hallway with 100 closed lockers. Um, so a man first opens all of them, and then he closes every second locker. So on the third pass, he toggles every third locker. So what this means is if it's already open, he closes it. If it's closed, he opens it. And
Okay.
then on the fourth pass, he does this for every fourth locker, and so forth. And then he does it for 100 passes. So at the end, he just toggles the 100th locker. So after he does all this, how many lockers are open?
Okay. He toggles every third locker, closes it. Okay. This process continues. So the initial case he's working with is like, let's use 0 to represent close.
Mm-hmm.